So before we were talking about geometric series. So if I think about a geometric series, we have something that looks like this. Oh, let's do it 0. Okay, so you have something like this, and we know that this converges when absolute value of r is less than 1. And so again, we want to remember that the a and r are numbers, and then that n is the variable up in the exponent. So this is the variable is appearing up in the exponent. That's how we can recognize it as a geometric series. Okay, so I know that that's going to converge. So well, let's think about this. What is that r? That r is a ratio that we're multiplying by to get to the next term. So in other words, if I did an plus 1 divided by an, what would I get? So I would get, oh, should I not use a there? I guess I'll use I don't remember what it uses in the book, but I'll call it b. I'll call it b just so we don't have two a's floating around. Okay, how about that? Okay, so an plus 1 is going to be br to the n plus 1 over br to the n. And when I divide that out, I get that that's just r. So in other words, to get to the next term in the series that we're adding, I multiply by r to get to the next term. And that's why this is looking like an exponential type function, because it's growing at this multiplicative rate. And if that r is less than 1, then that means that those terms are going to be getting smaller so fast that that sum ends up adding to a finite number. Okay, so let's talk about series that are not exactly geometric, but kind of act geometric. And so we're going to talk about the ratio test. And so what the ratio test does is it takes series that are not exactly geometric and it asks, how geometric do they become eventually? So we're going to look at this limit, this idea at the limit as n goes to infinity of an plus 1 over an. And we're going to see what that equals. And if that limit is some finite number, we're going to call it, guess what? Rho. Why? Because rho is r in the Greek alphabet, and it relates to this r here from the geometric series. So if it, over time, eventually, as n goes to infinity, if that approaches some rho, and rho is less than 1, then, we have absolute values here. Okay. And if that rho is less than 1, then we know that the series converges. Okay, and that's what the ratio test says. And similarly, the ratio test says that if that rho is greater than 1, what does that mean? Well, that means that those terms are, to get to the next term in the series, we're multiplying by something that's bigger than 1. So that's going to mean it diverges. And then we also get this inconclusive bit. If rho is equal to 1, then the test is inconclusive. And that doesn't mean that we don't know anything. It just means you need to use a different test. So, so that's how the ratio test works. So let me do a quick example. So the first example in the textbook, I'll just go ahead and copy that. Whoops. I was trying to write example, but I made a sigma. Okay, so let's look at this series, n equal 1 to infinity of 2 to the n over n factorial. And you will see a lot of times when you have a factorial showing up in your series that the ratio test is a good one, because when you do this computation with this an plus 1 over an, you kind of get rid of those factorials. And so we're going to show, we will use the ratio test. Okay, and so what we are going to look at is we're going to look at the limit as n goes to infinity of 2 to the n plus 1 over n factorial. And I'm dividing by that thing, oh, sorry, it should be n plus 1 factorial. Boop. And I'm going to divide by 2 to the n over n factorial. So I'm just going to write it as n factorial over 2 to the n. And then I start simplifying. Well, one thing to notice is, what do these factorials mean? So n plus 1 factorial is going to be 1 times 2 times 3 up to n, and then times n plus 1. So when I divide this out, I'm just left with the limit as n goes to infinity of, and there'll be an extra 2 on top because I have 2 to the n plus 1, and on bottom I'll have n plus 1. And so as n goes to infinity, the bottom of that is going to get bigger and bigger, so the whole fraction will be smaller and smaller. So that actually goes to 0, which means that the number that we're multiplying the terms by is going to be getting smaller and smaller as n gets bigger and bigger. And so those terms are going to, so we're going to end up having a convergent series. So by the ratio test, the series converges.